Our goal for today is to understand absolute value graphs and transformations of the absolute value parent function. So a parent function is the most basic function out of a function family, and we'll get to that in just a minute. But recall the absolute value written as those straight lines around x is the distance between a value and 0 on a number line. So here an example is shown of 5 units to the right of 0 and 5 units to the left of 0. So both of those values are an absolute value of 5 from 0. So just to recall how this works, absolute value of 4 is 4 because 4 is 4 units from 0. Absolute value of negative 4 is 4 because negative 4 is 4 units from 0. The absolute value of 4 is 4, but then the negative is on the outside. So your answer is 4 times negative 1, which is negative 4. And then this last one, negative 4, the absolute value of that is 4, but then we have a negative on the outside. So negative times the positive 4 from the absolute value bars. All right, so now let's graph the parent function for absolute value. It's just the most basic absolute value function you can have. So bars around just x. Nothing's added, subtracted, multiplied, or divided. So the way that we're going to fill out this chart is we're just going to think about each of these x values plugged into this function. So absolute value of negative 3 is positive 3. Absolute value of negative 2 is 2. Absolute value of 1 is 1. 0 is 0, and then 1, 2, and 3 will remain 1, 2, and 3. Again, that's just the positive value of the distance from 0. So now we're going to graph these points as an ordered pair. So negative 3, 3, negative 2, 2, and so on. Negative 3, 3, approximately in here. Negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2, and 3, 3. And if we connect those dots, we see the V shape that we've already talked about in previous videos, okay? And that will continue forever because we can plug any x value into this function and get an output, okay? So this trend will continue on both sides. This graph is symmetric, so meaning that we could cut it in half and we'd get the same thing if we folded it along or about the y-axis, because that's where I can cut it and it evenly fold together. So y-axis with a vertex at, so the vertex is either the highest or the lowest point. Here it's the lowest point, and that's at 0, 0. Going back to previous lessons, we're going to revisit domain and range. So domain is going to be all of your x values included in the function from left to right. So this function will go to the left forever, it will go to the right forever. The domain is all real numbers, so negative infinity to positive infinity. The range is not all reals because we have a low point that we do not pass, and that is at a y value of 0, and then we go up to positive infinity. So a bracket starting at 0, and then we go up to positive infinity. Again, we called this a parent function because it's the most basic absolute value function there is. All right, so now we're going to talk about transformations of this V shape, of this absolute value. These transformation rules will be the same for any parent function, but we will focus on other parent functions in the next lesson. So today we just want to focus on absolute value. But the rules stay the same for any function. You've got an A, an H, and a K. The A is going to be vertical stretches or shrinks. Think of it kind of like slope of a linear function. So a positive slope, the greater that it gets, the faster that the function grows. And then smaller slope, smaller growth. So if A is greater than 1, the graph is vertically stretched. I want you to think about taking Play-Doh or a piece of gum and stretching it out vertically. Think about it becoming more and more narrow. That's what's going to happen to this V. Here's the parent function. if the number of A is greater than 1, we're going to be stretching vertically, so we're going to become more and more narrow. If A is less than 1, like a fraction, so somewhere between 0 and 1, like 1/2, 1/3, 1/4, 2/3, the graph is vertically shrunk. We'll also see the word compressed. Those mean the same thing. Okay, so we're only worried about the actual value of A, not if it's positive or negative, up to this point. Now, if A is negative, the graph is vertically flipped or reflected. So if there's a negative in front of this A value, the V goes from here to here. It's upside down. Okay, and that's a vertical flip over the x-axis. The value of H tells us if we shift left or right horizontally. Okay, that's why it's an H for horizontal. Notice that this H is minus or subtracted inside the bars. Okay, that means that whatever you see as H is opposite of what you would think. All right, because negative just means opposite, right? So x minus 3, you might think, okay, well that's going in a negative direction, but it's not. The H value is just that 3. So the graph has shifted 3 units to the right. Okay, but opposite of that would be A plus 3. You might think it goes positive direction, but it does not. It's opposite. The H is negative 3, and we can see it broken apart here. It's like minus a negative is plus a positive. We've heard that before. Okay, so H is negative 3, meaning that we're shifting to the left 3 units. So in general, if you see a minus in a number, you're going right that many. Plus in a number, you're going left that many. And that is inside the absolute value bars with X. K is going to tell us if we go up or down. Okay, and notice that the plus K is here. So it's true to its sign. Whatever you see as the number, that's the direction you're going. So if you saw a minus 4, then you're going to go down 4 units. If you see a plus 7, you're going to go up 7 units. And that's all filled in for you here on the notes. So let's do an example where we find all of the transformations and then graph that transformed function. So we have g of x equals 2, and then x minus 5 in bars, and then minus 3. So notice this is not the parent function because the parent function would just be absolute value of x. We have transformations now. It's been shifted. The graph is shifted 5 units to the, it's going to be right because of that minus. 3 units down because the sign is true to the direction for the up and down. This means that the new vertex is, well, let's think about it. If our parent function has a vertex at 0, 0, and we are shifting every single point of this function, right 5 and down 3, then our new vertex is going to be at 5, negative 3. Okay, now we're going to look at the parameter A, or the component A. Since A is equal to 2, we will be vertically stretched by a factor of 2. Okay? Since we don't have a negative in front, the V is still going to be facing upward. It's not been reflected. And the way that we build this graph with this A value by hand, notice that this looks like 2 linear functions, right? One with a negative slope and one with a positive slope. And notice that the slope of those lines is 1 and negative 1, right? We're going up 1 over 1, up 1 over 1. Since our A is 2, now we're going to go up 2 over 1. So up 2 over 1, put a dot. Up 2 over 1 in the opposite direction, put a dot. And then that is enough information to go ahead and just sketch your V. Now, let's say you don't feel comfortable doing what I just did. That's fine. You've got Desmos. So you can go to Desmos and you can type in that function, 2, absolute value of x minus 5, and then minus 3. You can see a similar graph with a vertex at 5, -3. You could use those x-intercepts to help you graph. In this case, probably not too helpful since they're decimal values. But let's say that you want to switch that to a table so you can actually see points to graph. Well, then you would just do exactly what I did here. Press the settings button, change to a table, and then you can type in any x value you want, and it will give you the output. Okay? So if I want to do -2 back again, and then you can use as many points as you need to plot your graph. All right, and then of course the dotted line here was just your parent function, so that's just to compare your new function to. We can see that that's been stretched vertically. It got narrower. All right, and then the back of our notes. So this first example that we're looking at is example 2 on the back. Identify the transformations and graph the function a of x equals 2/3 and then x plus 1 in bars minus 3. So the x plus 1 means that we are traveling to the left 1. The minus 3 means we're traveling down 3. And then the 2/3 means that we are being vertically shrunk or compressed by 2/3. Again, we know it's a compression or shrink because this value is less than 1. Now the vertex is only depending on the transformation horizontal and vertical. It's not affected by the stretch or the shrink. So if I went left 1, my new vertex is -1, comma, down 3 would be -3 for the y value. So I can go ahead and plot that -1, -3. Okay, I know that my graph's going to be facing upward because I do not have a negative in front of the a value. And then I also know how to find more points of my v because of this 2/3. Think of that as slope. So you're going to go up 2, rise over 1, rise over run. So up 2, over 1, 2, 3. And then up 2, over 1, 2, 3 in the negative direction. So there is our rough sketch of our v. Again, if you want to verify that in Desmos, feel free to, or feel free to use Desmos to find other points. Now let's talk about domain and range of this function. So, domain of every absolute value function is going to be all real numbers. Okay, no matter the transformation, this graph will always travel to the left forever and to the right forever. No gaps in the graph at all. Your range will be affected by the transformations, okay? So I was shifted to the negative direction, down 3, and then my graph is facing up. So my lowest point is now -3 on the y-axis, and I touch it, and then I go up to positive infinity. All right, so I'm going to leave the next example for you to try on your own. Keep in mind that this negative on this 2 will flip the V shape upside down, okay? So your next points from your vertex will be traveling down instead of up, and that will affect your range as well. And you can see the completed problem in your guided notes answer key. And then real quickly, writing absolute value functions from a graph. I'm going to do this example on the left. I'll leave the right one for you to try. So the first thing I see is a vertex of 1, 6. That means I went right 1 and up 6. So I'm going to set that up as x minus 1 and a minus 6. Now I need to think about the a value. So this is flipped upside down. That means that this is going to have a negative a value. And that a value is all about the slope. Okay, so I go, if I think about any point on this graph, I'm going to choose this point right here. I rise 1, 2, 3, and I run 1. So that's going to be an a value of 3. And of course the negative comes from the direction of the V shape. You can make that f of x, a of x, b of x, it doesn't matter, or y equals, but make sure that you name your function somehow. So try those other 2 examples and then do your practice assignment for today's lesson.